In today's fifth presentation in the Progressive Network Design Consideration series, we're going to look at NATing, or Network Address Translation, what it is, when one should use it, and what the benefits are. But first, let's recap where we left off. We had identified all of the areas of automation for the purposes of network segmentation and to limit the majority of the traffic to only those networks. We then laid out the individual production lines in segmented and fault-tolerant rings, and our fault-tolerant plant backbone network, to which we redundantly coupled our individual production lines. Overall, this is an absolutely splendid design. It is robust and segmented, but it clearly cannot be this seemingly simple. Can it? Well, clearly not. Having done this, we now have a few dozen machines that are all on the network and able to see each other. While this is all well and good, we now have a problem. We have a lot of machines on the network and a lot of devices on the network. We also have vendor-assigned IP addressing schemes that are literally all over the place with very many common IP addressing schemes, most being in the 192.168.1 subnet. With around 500 IP-enabled devices and a plant expansion already in the discussions, this will not do. We cannot have duplicate IP addresses and different subnet classes. We need to do something, but reprogramming all of these devices would take weeks. To illustrate our issue in the blending and mixing line, we have several of the smaller machines in the production cells that are replicated six-fold. Each of these machines has a PLC with a 192.168.1.10 IP address, and an HMI with a 192.168.1.15 address, and so on. And there are 6 of these, all having the same IP addressing scheme. And this is replicated across all of the other production lines, some with the same subnet, some with others, and it's just an absolute mess. So, as you probably have already assumed by the title of this presentation, we're going to use NAT, or Network Address Translation, to help us solve our dilemma. It is really the only realistic option. But exactly what is NAT? NAT allows you to virtually translate one IP address to another, hence the name. And as far as NAT goes, there are theoretically 2 variants. The first is one-to-one NAT, which translates one IP address to a user-defined alternate IP address. One-to-one NAT is bidirectional by default, making it ideal for use within a network like ours. The other is IP masquerading, which is referred to as one-to-N NAT, and similar to one-to-one NAT, except that the outgoing traffic assumes the IP address of the NATing device, typically a router or firewall, doing the IP masquerading. IP masquerading is also unidirectional by default, only permitting inbound traffic with the appropriate firewall rules in place. An excellent example of this is your home's router that hides and protects your network from the internet. Given our need to only have select devices have their IP addresses translated so that they can communicate with the servers, while also being accessible from engineering workstations and hiding all of the other devices from prying eyes, one-to-one NAT is definitely the preferred solution that we're going to deploy in this network. To illustrate how this would be deployed, let's use the example of the plant, where corporate IT has mandated that the IP addressing be 172.16.16 with a 20-bit subnet mask, giving us an IP range of 172.16.16.1 to 172.16.31.254. This is a lot of IP addresses that we have at our disposal. We can subnet this further, and this is a best practice, by using a 255.255.254.0 subnet mask to yield 8 distinct subnets, each capable of 510 hosts or unique IP addresses. This is more than enough that we're going to need for each individual production line, as well as the rest of the plant's networks. This will allow us to assign a unique subnet to each production line, as well as the office and warehouse spaces. We will need to look at routing in a later presentation so that we can access all of these devices from a central location, and so that some select devices can also intercommunicate to others in other subnets. To create some consistency and uniformity, we will plan to configure NAT on machine 1 such that it will NAT to 172.16.16 dot something in the teens, and that machine 2 will NAT to something in the 20s in the same subnet, and so on and so forth. In our example, only the PLC and the vision system need to have access to the network, specifically the servers in the engineering space, while also being accessible from the network for programming and configuration purposes. In order for this to be possible, we're going to only NAT these two devices. We will configure the switch such that it will NAT the 192.168.1.10 to a 172.16.16.11, allowing that traffic to propagate out into the network. And we're then going to take the vision system, the 192.168.1.60, and we're going to NAT that over into a 172.16.16.12, and it will then be able to propagate out into the network. And obviously any incoming traffic, because the NAT is a bidirectional protocol, it is then going to allow the communication from the network to the PLC utilizing its NATed IP address, which is the 172.16.16.11. The switch will receive that, NAT it back over to the 192.16.16.10, and transfer that message over to the respective PLC. So, we've created some significant IP addressing housekeeping, allowing plant operators to easily know the IP addresses of any machine's given devices based upon which production line or network segment it is on and what machine number it is. We also now have ample spare IP addresses for when the time comes to expand our network, and we have tucked away those devices that do not need network access, only allowing those few devices through that truly need to communicate across the network. And we now have segmentation via subnetting and VLANs, and we've also added a good dose of security. But we have not yet addressed how to allow for inter-VLAN communication, which will require routing. And while the topic of networking and cybersecurity was going to be the next in this presentation series, we really need to finish addressing the rest of our communications first. And with that, we're going to leapfrog the topic of security for now and discuss Layer 3 and routing in our next video presentation in the Progressive Network Design Consideration series. Please join us then. Thank you for watching.